Section 5.2, Properties of Rational Exponents and Radicals. This is the first of two videos. What we're going to focus on in this video are reviewing exponent properties and then using those exponent properties, and then we're going to talk about simplifying radicals, kind of what we did in Chapter 3, way back when in Chapter 3, solving with square roots, but we're going to extend that to roots of higher powers, whether that's cube roots, fourth roots, fifth roots, whatever. So let's start with the exponent properties. There are 7 exponent properties. The definition, the property name, you can see there: product of powers, power to a power, power of a product. I would recreate this table in your notes, definitely. I don't really care if you know the names of these properties. What I care is that you know how to use them. So we're going to go through these definitions and then give you some examples. So the definition for product of powers, definition says if we have the same base and we are multiplying a to the m times a to the n, what we can do is we can add those two exponents. And when we add those two exponents, the bases do not change, m plus n. So for an example here, we could say something like, I'll do this in purple, we could say 3 to the 8th times 3 to the 7th becomes 3 to the 15th power. We would add 8 and 7. Or if we had a variable like x to the 4th times x to the 13th, that would become x to the 17th. Okay, for power to a power, that is if we have two exponents right next to each other. So if we have a to the m to the n power, what we do if we have two exponents right next to each other like these two, what we're going to say, or what we're going to do, is we're going to make this a to the mn power. We're going to multiply those two exponents together. So if we had something like 3 squared to the 4th power, this would become, let's try that again, 3 to the 8th power. Or if we had something like x to the 5th to the 3rd power, that would become x to the 15th power. Notice again, the base doesn't change, still 3, still x, just the exponents change. Power of a product, if we're multiplying two things together. So let's say we have a, b, and we're going to raise that to a power. What we can do, this is where an exponent becomes distributed. We can distribute that outer exponent of m to both parts. So it becomes a to the m times b to the m. So if we had numbers here, if we had something like 5 times 2 to the 3rd power, we could make this 5 to the 3rd times 2 to the 3rd. Now you're not going to see a whole lot of examples like this, but this is an example where if we do have numbers to a power, you can multiply this. Most people are going to make this 10 to the 3rd power, and that's what I would do too, but just showing you here that you can extend it to numbers. More than likely you're going to see it something like this. You're going to see xy to the 4th power. Let's say this becomes x to the 4th, y to the 4th. Okay, if you have a product raised to a power, then you can distribute that power to both parts of the product, or all parts of the product if there's more than two, and it distributes like that. If we have a negative exponent, what we're going to do, the negative exponent property allows us to make a negative exponent become positive. And there's kind of two parts to this. You can say that if we have a negative exponent, a to the negative m, you can make it positive by taking it to the opposite side of the fraction and then making it positive. Only the base and the exponent go. And when I say go, I mean switch sides, and the base does not change. If this was 3, this stays 3. If this is 5 or y, this stays 5 or y. The only thing that changes is the sign of the exponent. Okay, if your this is if your exponent is negative in the numerator. If your exponent is negative in the denominator, so we can make this, let's say 1 over a to the negative m. To make it positive, again, flip the side of the fraction. If it's negative in the bottom, we make it positive by taking it up top. The base goes but does not change, it stays itself, and then the exponent changes sign. So there's a couple of examples if you have a negative exponent, depending on where it's at. The two examples I'm going to give you are just if the negative exponent is in the top, but just understand there is that secondary part. So we could have something like 9 to the negative 2nd power. This would become 1 over 9 to the 2nd. If you wanted to evaluate it all out, it would be 1 over 81. If we had variables, something like x to the negative 4th, we can make this 1 over x to the 4th, and that's really all there is to it because we don't know what x is. So to make it positive, we switch which side of the fraction it's on. If you don't see a fraction like this one, assume that it is the numerator and take it down to the denominator. The next exponent property is by far the easiest one, the zero exponent property. And this says that any number to the 0 power, any base to the 0 power, is equal to 1. The only case where this doesn't work, this is a semicolon, a cannot be 0. 0 to the 0 power doesn't work. It's undefined. But any other number raised to the 0 power is 1. So if you had a number like 100 to the 0 power, that would be 1. If you had a variable, something like x to the 0 power, that's 1. If you had another negative, if you have a negative number to the 0 power, like negative 17 to the 0 power, this is still 1. Now, if you have a negative and then a number, so if you don't put the negative in parentheses, so if you had like negative 5 to the 0 power, this is going to be negative 1 because you're going to do the exponent first. You're going to do 5 to the 0 and then the opposite of that. So just be aware when you're taking a negative number, if you need to raise a negative number to a power, make sure you put it in parentheses so you know what specifically is being raised to the power. The sixth property here, the quotient of powers, very similar to product of powers way back at the top. That's for multiplying. This is dividing. If we have a to the m and we are dividing it by a to the n, what we're going to do here is we are going to subtract our exponents. The bases have to be the same, and we're going to subtract the exponents in the order of m minus n, the top number minus the bottom number. Okay, that never, you don't get a choice in that. It's always top number minus the bottom number. So if we had an example with, I'll just give you one with variables because you're going to see it that way most often. If you have x to the 13th over x to the 7th, this becomes x to the 6th. So take 13 minus 7 to get 6. The final exponent property is fraction to a power, and that says if you have a fraction a over b and we're raising it to a power, again, this is one of those places where you can actually distribute. The outer exponent goes to both the top and the bottom of your fraction. So it becomes a, oops, let me rewrite that a little better, a to the m over b to the m. So for an example, I'll do this one with numbers. If we had 9/4 to the second power, this becomes 9 squared over 4 squared. And if you wanted to evaluate that, if you wanted to, 81 over 16. But that's neither here nor there. So let's use these properties, and these aren't anything new. These are things you should have learned in Algebra 1. But what we're going to do now is we're going to extend these ideas to fractional or rational exponents. And we use the same rules. If we have the same base, like here in number 1, we have the same base, we're multiplying them. What we're going to do is we're going to add these exponents. Now, when we're adding fractions, we need a common denominator. So what we're going to do is we're going to rewrite this exponent with an exponent or with a denominator of 4, because if we count by 4s and count by 2s, the first number they have in common is 4. So this one's already 4, so this one's going to stay 4. So this is going to be 2 to the 3/4 power times 2. Now 1/2 becomes 2/4. You need a common denominator. Now 3/4 plus 2/4 becomes 5/4. So this is going to be 2 to the 5/4 power. And that's your answer right there for number 1, 2 to the 5/4 power. Now I'm going to do number 2 here in different color and do this one in purple. What I would suggest you do here, and really there are multiple options, what I'm going to do first is I'm going to look at this in the big picture, and I got a big fraction raised to a power. So what I'm going to do is I'm going to distribute this outer exponent of 3 to both the numerator and the denominator. So this is going to become, 20 to the 1/2 power to the 3rd power over 5 to the 1/2 power to the 3rd power. Now what I'm going to do, I've got two exponents right next to each other in both the numerator and the denominator. So this is going to become 20, let's see, 1/2 times 3 is 3/2. 5, let's see, 1/2 times 3 again is 5 to the 3/2 power. Now if you want, since these are both the same exponent, exactly the same exponent, what we can kind of think of is we can kind of think of what we did here, but go the opposite direction. We can actually undo distributing a 3/2. So we can make this 20 over 5 to the 3/2 power. And then the last thing we can do, we can actually do 20 divided by 5, and we get 4. So this becomes 4 to the 3/2 power. Now we can actually go even farther with this, thinking about what we did in section 1, where if we have a fractional exponent, 4 to the 1/2 power, same thing as the square root of 4. So this becomes, so we'll rewrite this as square root of 4, that's the 1/2 power, to the 3rd. Square root of 4 is 2, to the 3rd power gives us 8. So this actually simplifies down into one nice number of 8. Now, the first one didn't simplify because the 1/4 power, the 4th root of 2 is not a good number. It's not a whole number, so we don't need to worry about doing that. If you get to the point where you can't do anything, like 2 to the 1/4 power, I would say you're done. But this would be a case where we could keep going, and eventually we got a whole number. Let's try another one here. Number 3. 3 over 3 to the 1/4 power. The top number, the 3 here, this does need an exponent. We can assume that if there's not one, we can assume that it's 1. So we can say 3 to the 1st over 3 to the 1/4. This is going to be using that quotient of powers property. We have the same base. They're both 3's. And we're dividing. That's what the fraction bar tells us, so we need to subtract. So what we need to do first is we need to make sure we have a common denominator. In this case, we can kind of think of this as 1 over 1. This would be 4. Our common denominator here would be 4. So we'll say 3 to the 4/4 over 3 to the 1/4. And we have a common denominator, so we just subtract. This becomes 3 to the 3/4 power. Again, the 4th root of 3, the bottom number tells us the root. The 4th root of 3 is not a good number, so I would say this is what we're going to leave it as straight away, and that's going to be our final answer. The last one here, 5 to the 1/3 times 7 to the 1/4. Big picture, we got something times something else, so that's a product. We're raising that to a power. This would be an example where we could distribute that outer exponent of 3 to our product. So this becomes 5 to the 1/3 to the 3rd times 7 to the 1/4 to the 3rd power. And then we can use our power to a power property where we have two exponents right next to each other. 1/3 times 3 is just 1. So this becomes 5. Whoops, let me go back to the pen. 5. Let me redo that in purple. 5, and this would be 5 to the 1st. You don't necessarily have to write the first power. If it's not written, it is assumed that it's the first power. Times, let's see, 1/4 times 3 would give us 3/4, so we'll say 7 to the 3/4 power. And really, that's all we're going to be able to do because, again, we don't know the 4th root of 7, and times 5 really doesn't help us either. So this right here is our final answer. The second part of this video is oversimplifying radicals. What we're going to do is when we talk about simplifying radicals, we've already done some of that. We've talked about simplifying square roots, but now we're just going to extend those square root properties to higher roots. So 3rd root, 4th root, 5th root, 10th root, 100th root, whatever it might be. We can use those same two properties, the product property and the quotient property. If you remember from chapter 3, the product property says if we have the square root of a product, square root of A times the square root of B, what we can do is we can break that up into two square roots, the product of two square roots, make it the square root of A times the square root of B. Well, now when we've got something else, let's say we had the cube root of AB. It works exactly the same way. We can make this the cube root of A times the cube root of B. Whoops, B, let's try that again, there, B. And if this was a 4, then these would both be 4s. If this was a 6, then these would both be 6s. But I'm just kind of giving you something that's a little bigger than a square root. The quotient property, if you remember, talked about the square root of a fraction, square root of A over B. We could split this up then into the square root of A over the square root of B. Again, we can do the exact same thing with higher degree or higher index roots. So if we had something like the 5th root of A over B, we could make this the 5th root of A over the 5th root of B. So I'm just showing you that it extends to both. And what we're going to do is we're going to put these radicals into simplest form. Now, simplest form means three things. No radicals. None of the radicals that you have perfect powers as factors. So remember, when we talked about square roots, if we had something like the square root of 8, we could make this the square root of 4 times 2, which then became 2 square root of 2. That would be an example of simplest form. No perfect powers left underneath the radical. Okay, no fractions under the radical and no radical in the denominator of a fraction. Those are pretty straightforward, and we have a couple of examples here where we're going to have to deal with that, and I'll show you how to do that here in just a second. So let's try simplifying. The first one's pretty straightforward. The cube root, not square root, cube root of 135, the 3rd root of 135. Now 135, if you look at that table I gave you with all those perfect powers, you're not going to find 135 in the n to the 3rd column. So what we need to do is we need to find a number that divides 135 that is in that end of the 3rd column. And that number that does divide 135 evenly in that end of the 3rd power column is 27. So we can rewrite the cube root of 135 as 27 times 5. Now, what we can do is we can use that product property to make this the cube root of 27 times the cube root of 5. The cube root of 27 is a nice number. Okay, it is 3. So this becomes 3 times the cube root of 5. We don't have any fractions, so we don't have to worry about the last two. No radicals have perfect powers as factors. 5 is not a perfect cube, and it's not divisible by any of the perfect cubes. So we are done. This is in simplest form. 3 times the cube root of 5 is your answer here for number 1. For number 2, sometimes it's going to be more beneficial if you actually make one single radical rather than try to break it into 2. 4 is not a perfect cube. 128 is not a perfect cube either. So what we can do is we can actually multiply these two together. 4 times 128, and what that's going to give us is the cube root of 512. 4 times 128 is 512, and conveniently, 512 is in that end of the third column. 512 is a perfect cube. The cube root of 512 is 8, and that is your final answer for number 2. It's pretty straightforward. Sometimes it's easier to go backwards than to try to make it even smaller. Okay, does that mean that's the only way to do it? No, not at all. You could try to break this one down and then multiply it with whatever's left. Eventually you would get to 8, but sometimes that's too many steps or more steps than what's actually required to get to your final answer. Number 3, fifth root of 192 over the fifth root of 6. Again, this is one where maybe it's more beneficial to combine our roots because we've already split this thing into a fraction and they have the same root, which tells us that if we look back at this is basically going from here. What we're going to do is we're actually going to combine them into one square root with one fraction. So I'm going to make this, do this in green here. We're going to make this the fifth root of 192 over 6, and 192 divided by 6 is actually a fantastic number. It's actually 32. So we'll have the fifth root of 32, which conveniently enough, 32 is in that n to the fifth column, and when you look all the way to the left from 32 and into the fifth, what you're going to find is that the fifth root of 32 is 2. And that's it. That's your answer right there, just 2. Let's try another one here. Number 4. This is an example where we're going to have to do some manipulating. Okay, 19 is not divisible by 4, just like we were going to do here. That doesn't work in this case because 19 is a prime number. It's not divisible by anything other than 19 and 1. So what we're going to do, so we need to worry about no fractions under the radical. Well, we don't have to worry about that right now. We don't have any fractions underneath our radicals, but we do have a radical in the denominator of our fraction. So what we need to do is we need to come up with a number, or we need to manipulate this so that the bottom number is a perfect fourth power. So the perfect fourth powers would be 1, 16, 81, 256, and so on. So what we can do, we don't always have to multiply by the same number, but this is an example where it makes sense to multiply by the fourth root of 4 over the fourth root of 4. Because what's going to happen here is that when we multiply these together, the bottom number becomes the fourth root of 16. Pardon the bell in the background there. We haven't changed the value of this fraction. We're multiplying it by 1. We're just changing its appearance. Now, if we're going to multiply these two numbers, we should probably multiply these two numbers as well. 19 times 4 is 76. So this becomes the fourth root of 76. Now, we still have radicals in the denominator, but it works out really nicely because 16 is a perfect fourth power. The fourth root of 16 is 2. Now, 76, not a perfect fourth power. It's not divisible by 16, and 81 would be the next one, and that's too big. So really, if we can't do anything with this, then we're going to leave it just as is. This is going to remain the fourth root of 76, and that's going to be your final answer right there because we've met all of our requirements. We don't have any perfect powers, we don't have any fractions, and we don't have any radicals in the bottom of our fraction, so we are done right there. Final example here, the fifth root of 7 over the fifth root of 8. Again, we don't have any perfect power factors, so we don't have to worry about that, but we do have this radical in the bottom. And once again, the idea is that we don't want any radicals in the bottom, or we want this to be a perfect, in this case, fifth power because we're working with fifth root. So we don't always have to multiply by the fifth root of 8 over the fifth root of 8 because 8 times 8 is 64, and 64 is not a perfect fifth power. It's not a number that's got a perfect or a good fifth root. So what we're going to do, I'm going to switch to orange here. We're still going to have to multiply, but we don't necessarily have to multiply by the same, when I say the same number, I mean it doesn't always have to be this. Now, in this case, it worked out to be the same number, but it doesn't always have to be that way. Now, if I look at the fifth root or the fifth powers on that table I gave you, what you should see is that ideally we'd want this to be a perfect fifth root. Root of 3, that needs to be a 5, so this needs to be a perfect fifth root. And again, this is also going to be a fifth root when we multiply. Now, 8 times what gives me a perfect fifth root? Well, 8 is divisible by, or 8 goes into 32, which is a perfect fifth power. or a number that's got a nice fifth root. So what we're going to do is we're actually going to take this times 4. So if we're going to take the bottom number times 4, then we also need to take the top number times 4. So what we're going to have then is the fifth root of 28 over the fifth root of 32. 28 is not a perfect fifth power. It's not divisible by any of the perfect fifth powers, so it's going to stay the fifth root of 28 on the top. Let me try that again here. We'll make that a little better of an 8. That's not much better. Let's try one more time. 28, there we go. And then the fifth root of 32 is a good number. It is 2. Now, are you always going to have 2 on the bottom like we had with these two? No, not necessarily. You could have 3, you could have 4, could have 10, whatever it might be. But just understand that you don't always have to multiply by the same number. These two numbers don't have to be the same. These two do, but these two do not have to be the same number. It could be 8 and 4, could be 4 and 4. It's just going to depend on the situation. But 28 is not a perfect fifth power, not divisible by any. We don't have any square roots or radicals in the bottom. We don't have any fractions underneath the radical. So we are done right there with the fifth root of 28 over 2.